So this video is the third video on chapter 4. It will focus on isotopes and ions. So all atoms of the same elements have the same number of protons. For example, all carbon atoms have 6 protons in their nuclei. You find this number above the symbol in the periodic table when you look at the elements. There is a whole number above the symbol, and that is the number of protons for an element. And so the number of protons in the nucleus of an atom is called the atomic number. And we use the capital letter Z to designate the atomic number. And so Z is also the number of protons. And because each element's atoms have a unique number of protons, each element can be identified by its atomic number. So that atomic number is unique to each element. And the elements are arranged on the periodic table in order of their atomic numbers, from left to right and then from top to bottom. So the same element can have atoms with different masses, which are called isotopes. So this is a part of the Dalton atomic theory that has been changed. He thought all atoms of an element were exactly identical, but actually they may have different masses. And so we call those isotope. Isotope comes from the Greek prefix iso, which means same, and topos comes from topos, place. So isotopes of an element occupy the same place in the periodic table. So they are represented by an element. And so, for example, neon has 3 stable isotopes that we can find in nature. And so that's why they are stable. And there is neon 20. The 90.48% means it's found at 98.48%. When you find a sample of neon, you know, more than 90% are neon 20s. Neon 21, more like a trace isotope here because it's 0.27% abundant. And then neon 22 would be abundant at 9.25%. So when you find a sample of neon, you would find those 3 isotopes within the sample of neon with those different percent abundance. And so if you take the mass of your sample of neon, the observed mass would be a weighted average of the weights of all the naturally occurring isotopes. So all stable isotopes, and here there is 3. You take the contribution of each isotope and you add them together, and that gives you a weighted average. And it's also called the atomic mass of neon. And in the periodic table, these numbers are located below the symbol or the name. And these numbers are always with decimals. And here for neon, it would be 20.18 AMU. AMU means atomic mass unit. And so the atomic mass unit is obtained by taking the contribution of the neon 20, which has a mass of 19.9924 AMU, and you multiply by its percent abundance divided by 100. And so this 0.9048 is the decimal form of the percentage. Then you take the contribution of neon 21, which has a mass of 20.9938 AMU. You see that this is almost 21 AMU, multiplied by 0.0027, which comes from the 0.27% divided by 100. And then you add the contribution of neon 22, which has a mass of 21.9914 AMU. You can see it's almost 22 AMU, multiplied by the percent abundance divided by 100, and that comes to 0.0925. So you calculate those contributions and you add them together. And then that's how you come up with the 20.18 AMU, which is the average mass for an atom of neon. So the existence of isotopes was first suggested in 1912 by the radiochemist Frederick Soddy, based on studies of radioactive decay chains, which indicated about 40 different species described as radio elements or radioactive elements that were between uranium and lead, although the periodic table only allowed for 11 elements from lead to uranium. And so it's only by J.J. Thomson that the first evidence for isotopes of a stable, which means a non-radioactive element, was found. So J.J. Thomson, if you recall, is the scientist who discovered the electrons within the atom. So he found the presence of isotopes even in stable elements or non-radioactive elements. Let's look at an interactive periodic table to see what we mean by isotopes. So this is an interactive periodic table, ptable.com, so easy to find. And here we selected the isotope tab. And you can see the periodic table with colors here. And each element has several isotopes. For example, if you look at hydrogen, the atomic number 1, the symbol H, hydrogen is the name, and then the little 7 here at the bottom of the square indicates that hydrogen has 7 isotopes. And so if I click here, I can see the 7 isotopes of hydrogen. And according to the legend here, elements or isotopes that are stable, and so that means you will find them in nature, are surrounded by a black line. And so here, hydrogen is having 2 stable isotopes, hydrogen 1 and hydrogen 2. After that, you see it changes color, and this indicates, radioactive activity, neutrons emissions, beta decay, and so on. So hydrogen has 2 stable isotopes, hydrogen 1 and hydrogen 2, for example. Carbon, another example, has how many? 15 isotopes, but there is only really, so carbon 12 is a stable isotope, carbon 13, another stable isotope, and carbon 14 is also considered a stable isotope, because if you look here at carbon 14, you can see that the half-life, so if you look at this line here, the half-life of carbon 14 is 5,700 years, which means if you start with a sample of 100 grams of carbon 14, let's say, and it's T0 times 0, and then you wait 5,700 years later, you will have only 50 grams of carbon 14, and the rest, the other 50 grams, would have been decayed. And so here carbon 14 is a beta decay. Given the blue color here, we have a beta decay happening for carbon 14, and so those atoms change into another atom. The nucleus changes. But so those 5,700 years are so long that it's considered stable. But you can give it a half-life. For example, the next carbon isotope, carbon 15, has a half-life of 2.5 seconds. So this one is really unstable compared to carbon 14. And you can look so on, you know, like carbon 17 here has a half-life of 193 milliseconds, so very unstable. Also going through a beta decay. And so you see that all elements here have, you know, so for example, helium 9 isotopes, neon 19, iron 28, calcium 24. All elements have isotopes and a lot of isotopes, but very few of the isotopes are actually stable, and it's when you have stable isotopes that you can find the element in nature, and you will find those stable isotopes only. Let's look at uranium. Uranium has, how many was it? 20, yeah, can't see it anymore, but 26, maybe 26 isotopes, you see, and there is none of them that is stable. All of these here in yellow are overcoming alpha decay and electron capture, and then some overcome beta decay. Okay, so you can play with that and look at it more carefully. You can also use this periodic table, you know, to look at properties of elements, their electron structures, and what kind of compound they make. So the website was www.ptable.com. So nice interactive periodic table there. So isotopes. All isotopes of an element are chemically identical, right? They undergo the exact same chemical reactions. It doesn't change their chemical reactivity. All isotopes of an element have the same number of protons. Otherwise, you cannot call them by that element's name anymore, right? The number of protons is the identity for an element. So all of its isotopes have that same number of protons. What changes between isotopes of an element is the mass. They have different mass, those isotopes. And isotopes of an element have different mass because they have a different number of neutrons. It's the number of neutrons that changes the mass of each isotope. And neutrons only contribute to the mass, don't contribute to charge, like protons or electrons. And so isotopes are identified by their mass number. And the symbol we use to represent the mass number is capital A. So capital A is calculated by taking the number of protons plus the number of neutrons of each isotope. So each isotope will have its own mass number because they will all have the same number of protons for a given element, but the number of neutrons will vary. So then the mass number will change for each isotope of an element. And so we have a way to symbolize isotopes, and it's shown here on the upper right corner. So you use the symbol of the element represented by capital X here. Then in the upper left corner, you will write the mass number. So the capital A is the mass number. Remember, the mass number is the number of protons plus the number of neutrons for that isotope. And so because it's number of particles, it's a whole number, an integer. And then in the lower left corner, you will find the atomic number. The atomic number represents the number of protons for that element. Notice how that the fact that you have the element symbol, you can find in the periodic table the atomic number of that element. So you could do without the Z there, right? So Let's look at an example. Let's look at the isotopes of carbon. We said we had the 3 isotopes, stable isotopes for carbon. Carbon 12, carbon 13, and carbon 14. So because it's all isotopes of carbon, they all have 6 protons in their nucleus, right? The 6 here, atomic number, goes with the capital C for carbon. Because we are talking about neutral atoms here, so they will have the same number of electrons as they have protons, so 6 electrons, because those 6 electrons will cancel out the 6 positive charges from the protons. So then we have all neutral atoms. Then to find out the number of neutrons, you do the mass number minus the atomic number. So the top number minus the bottom number, and that gives you the number of neutrons. And so for carbon 12, you do 12 minus 6 protons, it's going to be 6 neutrons. For carbon 13, you do 13 minus 6, and it's 7 neutrons in carbon 13. And carbon 14 has 8 neutrons, because you do 14 minus 6, and that's 8 neutrons in the isotope carbon 14. So that's how, by having this symbol, you can retrieve the number of protons, neutrons, and electrons. And below that, we have the percent abundance for each isotope. So carbon 12 is the most abundant of the isotopes of carbon, 98.89%. So when you find carbon, you will find it's mostly carbon 12. Then 1.109% are carbon 13. And 10 to the negative 10 are carbon 14. As you know, carbon 14 has a half-life of 5,700 years. So it, decays, and so it's that's why its abundance will get smaller and smaller. And it's used to actually identify old things, very old things, because all matter, a lot of the matter has carbon, and by finding the ratio of isotopes within that sample, you can go back to the age of the artifact, for example. So that's the isotopes of carbon. So let's do a concept check where we will calculate the atomic number, the mass number, find out the number of protons, number of neutrons, and number of electrons for given isotopes. And so we just saw how an isotope can be given by this symbol, where you have the mass number on top, the atomic number on the bottom to the left of the symbol. But there is another way also of writing isotopes. It's by giving the element symbol or name dash mass number. So that 37 here after K is the mass number. So let's do this together. Well, I would like you first to pause the video, try to find out on your own what are those atomic numbers, mass numbers, numbers of protons, neutrons, and electrons on your own. And then watch for the answer. So I'm going to go over the answer for those who are ready to watch it. So isotope of B is boron. If you look at the periodic table, B is boron. It's atomic number 5. You can see that from the 5 written in the lower left corner. 5 here represents the atomic number. So that's going to be 5 for the atomic number. We also know that atomic number 5 represents the number of protons. So you can also write 5 protons. And here there is no charge. It's neutral atom. So you can also already say you have 5 electrons in that isotope. Now, the mass number. The mass number is the number in the upper left corner. So here it's 11. So now we have only the number of neutrons to calculate. And so the number of neutrons plus the number of protons equals the mass number. So if you do mass number minus number of protons, you will get the number of neutrons. And here it's mass number 11 minus 5 protons equals 6 neutrons. So there is 6 neutrons in this isotope. Next, uranium-235. So U is for uranium. It's atomic number 92. We see it in the lower left corner here. So atomic number 92, which means we have 92 protons in this isotope. And because it's a neutral atom, we also have 92 electrons, because the number of electrons must equal the number of protons for the atom to be neutral. The mass number is the number in the upper upper left corner, so that's 235 is the mass number for uranium 235. And the mass number equals the number of protons plus the number of neutrons. So to calculate the number of neutrons, you do the mass number 235 minus 92 protons equals 143 neutrons. Okay. Next, we have K37. K is the symbol for potassium. Potassium 37. Here you're given only the mass number. That's 37 here is the mass number. So mass number 37. That's the mass number. To get the atomic number, we will look into the periodic table for potassium. And potassium, above its symbol capital K, there is a 19 here that indicates 19 protons for potassium. I will erase that if possible. Okay, so from the atomic number, we can deduce the number of protons, and that's 19 again. Here again, it's a neutral atom, so you can write 19 for the number of electrons, so that the atom is neutral. Now, to calculate the number of neutrons, you do the mass number, which is 37 minus 19 equals 18. So we have 18 neutrons in K37. O17. O is oxygen. So if we look at the periodic table, oxygen has an atomic number 8. So we can write atomic number 8, which is going to mean 8 protons. And because it's again a neutral atom, it's 8 electrons. The mass number can be found by the number after the dash here, and it's 17, oxygen 17. So now, if we want to calculate the number of neutrons, you do the mass number 17 minus the number of protons, 8, equals 9 protons for oxygen 17. So that solves this concept check. Sorry. Oops. Oh, I need to hold on. Okay, so let's move on. Now, we will talk about charged atoms. So, the number of protons determines the element. Now we know the number of protons identifies elements just as their symbol or name does it. For example, all sodium atoms have 11 protons in the nucleus. If you look at the periodic table, atomic number for sodium is 11. So they all have 11 protons in the nucleus. In a chemical change or chemical reaction, the number of protons in the nucleus of the atom does not change. You cannot change the number of protons by undergoing a chemical reaction. There is no transmutation during a chemical change. However, during radioactive or nuclear changes, atoms do change into a new type of nucleus, and so a new type of atoms and elements. But the main focus of this course is going to be chemical reactions. And during those chemical reactions, there is no way that your element is going to change after the chemical reaction. Atoms in a compound are often electrically charged, and so we call these ions. So how do we make ions? Atoms acquire a charge by gaining or losing electrons, not protons. We just said the number of protons cannot change, right? It's giving you the identity of the element, and that identity cannot change when atoms become ions. So what changes then is the number of electrons. Ions with a positive charge are called cations. So cations here, the name suggests, the T here suggests a positive sign. So ions with a positive charge are called cations. And so they are made by losing electrons. The atom will lose electrons because you cannot change the number of protons. So for the atom to have an excess of positive charges, it needs more protons than electrons. And for this, it needs to lose electrons. And then you will have some protons and positive charges in excess and obtain a cation, a positive ion. Ions with a negative charge are called anions. And here, as a mnemonic, here there is an N for negative, right? N for negative. And so atoms becomes negative ions by gaining electrons. Again, you cannot change the number of protons. So for the atom to have an excess of negative charges, you need more electrons than you have protons. Because you cannot change the number of protons, then the atom will have to gain electrons to accumulate negative charges and become an anion. So chemically, ions are very different from the neutral atoms, because you will see that chemical reactions, they all are depending on the number of electrons in the atoms. The number of electrons changes the structure of the atoms very much, and that's what matters when you are reacting or changing an atom into an ion. So then the properties of the ions are very different from the neutral atom they came from. So let's look more closely at cations. So for each positive charge, the ion will have one less electron than the neutral atom, right? So let's look at the sodium atom. Sodium, atomic number 11, has then 11 protons and 11 electrons, because it's neutral, right? So it has to have the same number of positive and negative charges. The sodium ion Na+ has still 11 protons because it's still sodium, so you cannot change the number of protons. But now, to have this excess positive charge here on sodium, you have to have lost an electron. So instead of 11 electrons now, it should have only 10 electrons. And this way, 10 of the electrons will cancel 10 of the positive charges from the protons, and one of the positive charge, will not be cancelled anymore and will show up as a positive charge on sodium. And so sodium will become the cation Na+. So one way to write this, in the way chemists do, you can show that the sodium atom, Na, becomes the Na plus ion plus one electron that is lost. If you put them together, you see that you're going back to a neutral atom. If you put the electron back to the sodium ion, it's going to be a neutral atom again. Another example with calcium. Calcium, atomic number 20, so it has 20 protons and 20 electrons to cancel out those 20 positive charges. And so calcium likes to make the calcium 2 plus ion. Calcium 2 plus ion still has 20 protons because it's still calcium, and calcium has 20 protons. But to get those two positive charges, the calcium atom must have lost 2 electrons. 2 electrons must be gone, and so that means from 20 electrons it goes down to 18 electrons for calcium 2 plus. This way, 18 electrons cancel the 20 positive charges cancel 18 positive charges on the protons, and you have 2 other protons that are not cancelled out. The charges are not cancelled out, and they show up in the ion calcium 2 plus. So another way to write this chemically is to show the calcium atom on the left, then an arrow to show the change into the calcium 2 plus ion plus 2 electrons that have been lost by calcium. Same way, aluminium can lose 3 electrons and become the aluminum 3 plus ion. For anions and negative ions, because the number of protons cannot change, so that means the ion will have 1 more electron per negative charge than the neutral atom. So let's look at chlorine. Chlorine, atomic number 17, has 17 protons and 17 electrons when it's the neutral atom. If you make the chloride ion with 1 negative charge, that means you still have 17 protons because it's still chlorine, but you've gained an electron, and so you have from 17 electrons you go up to 18 electrons for the chloride ion, and that 1 extra electron will not be cancelled by a proton, and that's why it shows up as a negative charge on chlorine. So the way to write this chemically is this time you have the chlorine atom, you give it an electron, so it's going to be on the left side of the arrow. The arrow shows that it becomes the Cl minus anion, right? Because chlorine gained an electron and became the negative ion, Cl minus. Another example with sulfur. Sulfur, atomic number 16, has 16 protons and 16 electrons. Sulfur likes to become the negative 2 ion, the sulfide. Sulfide has still 16 protons because it's still sulfur. But to get those 2 negative charges, it needs to have gained 2 electrons. So from 16 electrons, it goes up to 18 electrons. And so writing this chemically, we show that the the sulfur atom gains 2 electrons. So you add it to the left here of the arrow, plus 2 electrons, give the anion sulfide S -2. And we could show another example with nitrogen. Nitrogen likes to become the N-3 ion. It likes to gain 3 electrons. And so they will show up as 3 negative charges on the nitride ion. So let's practice writing or finding out the number of protons, electrons, and neutrons for isotopes of ions this time. It's not neutral elements anymore, we have ions. So again, I would like you to pause the video, work this out on your own before you watch the answer. So for those who are ready to watch the answer, we have Cl minus 35 and then 17. 35 is the top number, here is the mass number. And the 17, the bottom number, here is the atomic number. Remember how the atomic number is the number of protons. So you can write here that this isotope of Cl minus has 17 protons. Now let's calculate the number of electrons. So we see that it's an ion, it has 1 negative charge. So you would start with 17 electrons if it was neutral. But then there is 1 extra negative charge, and those negative charge come from the electrons. So you have to add, 17 plus 1, and it's going to be 18 electrons for Cl -1, because it has that extra charge here, which indicates it has gained an electron from the neutral atom. And then for the number of neutrons, you do the mass number, which is the top number, minus the bottom number, the atomic number, or the number of protons. And that's a difference of 18. So this isotope of chlorine has 18 neutrons. Let's look at the other example. Ba is barium 2+, 138 and 56. So if you look at the periodic table, barium has an atomic number of 56, and this is indicated by the bottom number. This atomic number is the number of protons. Now, the number of electrons in a neutral barium, it would be the same number of electrons than we have protons, so 56. So we would start with 56. However, we have 2 positive charges there. 2 positive charges means we have 2 protons in excess compared to the number of electrons. So we need to remove those 2 electrons, 2 electrons to get the number of electrons that the barium 2+ ion has. So it's 54 electrons. Why? Because there is 2 protons that are not cancelled out by electrons, right? Those 2 pluses there are not cancelled out by electrons. So that means there is less electrons than protons. So you need to remove those 2 charges from the total number of protons. And then for the neutrons, you take the mass number, which is 138, the top number, minus the bottom number, which is the number of protons, equals 82 number of neutrons for this isotope.